Well, thank you very much. My name is Kevin Schaefer, and I want to talk about emissions from thawing of permafrost. I think it's my responsibility. Can you hear me? I think it's my responsibility as a scientist to try to explain our research results to a broader audience. I really appreciate the invitation. Thank you very much. I'd also like to note that the picture up here from Barrow, Alaska, probably is closer to what I normally look like. I normally don't wear a suit. Now, some background. Permafrost is permanently frozen ground. And to try to illustrate what permafrost actually looks like, this is a profile of permafrost exposed by erosion on the north slope of Alaska on the Arctic coastline. At the very surface, you've got vegetation, which is typically grass and moss. Underneath the vegetation, you have what's called the active layer. The active layer is the surface layer of soil that thaws in the summer and then refreezes in the winter. Around this region, the active layer depth is anywhere between 30 and 40 centimeters deep. Underneath the active layer, you have the permafrost. Now, permafrost covers roughly a quarter of the northern hemisphere land surface. The thickness of the permafrost layer is a balance between freezing from the surface and warming from the Earth's interior. Along the Arctic coastline, the permafrost is deepest, ranging from 700 meters to as deep as 1,500 meters deep. As you go further south, the temperatures are warmer and the permafrost gets thinner until along the southern margins, the permafrost is only about 50 to 100 meters deep and often very patchy. Now, to get an idea of the current status of permafrost, I want to show you some temperatures of permafrost for a transect of monitoring stations that cut Alaska from north to south. Now, these are what are called boreholes. A borehole is simply a hole that's drilled down to a couple hundred meters depth, and you lower a temperature sensor or a thermometer in there and measure permafrost temperature as a function of depth. On the right, you have the observed temperatures. On the horizontal axis, you've got year. And the vertical axis, you have temperature at a depth of 20 meters. Now, there's a couple of things to notice about this right off, is that the further north you go, the colder the temperatures. And this, of course, makes perfect sense because the further north you go, the colder the air temperatures are. So it's reflecting the air temperatures. Another thing to notice right off is that the temperature at every single one of these stations is increasing over time. And the increase in time is greatest at the northernmost station. The northernmost station, West Dock, which is black here, has increased roughly 2 degrees over the last 30 years. Now, the thing to realize about permafrost is that nothing happens fast in permafrost. Down at depths of 200 meters, the temperatures are still responding to the little ice age 400 years ago. So when we see a 2-degree temperature increase at 20 meters depth, we find that quite alarming. Now, to go out into the future, this is an animation of simulated active layer depth, or maximum depth of thaw, as a function of time. And you can see in the upper right is the year clicking by. And on the color bar there is the thaw depth, color-coded in centimeters. The black areas are areas where there is no permafrost. Now, as the temperatures go up over time, the first thing you notice is that the black areas, the areas with no permafrost, are getting greater and greater. And we're starting at the southern margins of permafrost and moving north. This, of course, makes sense because along the southern margins, the temperatures of permafrost are greatest and they're closest or more vulnerable to thaw. Another thing to notice is that as time goes on, the colors change from green and yellow to orange and red. And what that means is that the depth of the thaw is getting deeper over time, which of course also makes sense. The warmer the air temperature, the deeper it's going to thaw. So in looking at this animation, you just walk away with two things. As permafrost degrades over time, it's going to thaw from the south to the north and from the top down. Now, permafrost is like concrete. The ice within this permafrost acts like cement to bind the soil particles together. Permafrost is hard, tough, and very durable. And to illustrate this, this is a colleague of mine who was drilling to get some soil samples to take back to the lab to analyze, and he accidentally froze his drill bit into the permafrost. And he had to go back into Fairbanks to rent a jackhammer to get this drill bit back out. Now, like I said, frozen permafrost is really tough. But if you thaw out the permafrost, the ice changes to water and the permafrost changes to mud, which is very weak. And this has a lot of implications for human-built infrastructure in the Arctic areas. And to illustrate this, I'm just going to show a couple of examples. In the upper left, you see an apartment building that's built in Russia. And underneath the foundation, the permafrost thawed, it sagged, and the entire building collapsed. The collapse occurred within 24 hours after the first cracks started appearing. On the bottom left is a village along the coast of Alaska. And now, as was stated previously, as the ice has retreated to the north, the wave action has gotten much bigger and much stronger. And coupled with the fact that the permafrost is warming up, it made this very vulnerable. And the waves literally eroded the village away. It fell in the ocean, and this village actually had to be moved. But it's not just human infrastructure where thawing permafrost has an impact, it's the ecosystems itself. To illustrate this, on the upper right is a lake in central Alaska. Now, in this part of Alaska, the permafrost is only about 100 meters thick, and underneath the lake typically is a thaw bulb, which is just basically a layer of mud that doesn't necessarily refreeze in the winter. As temperatures have gone up, the thickness of this thaw bulb has increased, and eventually it penetrated through the entire permafrost layer to reach the groundwater underneath, and the entire lake drained from below, kind of like pulling a plug in a bathtub. Now, in the lower right here is features called thermal karst. Now, permafrost typically contains huge blocks, layers, and wedges of pure ice. When permafrost thaws out, this ice melts, and the water drains away, and the ground above it literally collapses. And this is a thermal karst feature on the north slope of Alaska near the Alaska pipeline. You can see in white there is the ice layer that's retreating. And as that ice wall retreats, as it melts away, the ground above it simply collapses. And you can imagine after a thermal karst, after the ice melts, this area is very vulnerable to erosion. And this kind of activity is actually a major agent of change in the permafrost regions. Now, I've been talking about the effects of climate change on permafrost, but it's possible for thawing permafrost to impact global climate. And the reason is that there's roughly 1,700 gigatons of carbon frozen into the permafrost. To give you an idea of how much this is, the atmosphere currently contains roughly 750 gigatons of carbon. So this is literally, there's literally twice as much carbon frozen in the permafrost as there is in the atmosphere today. Now, this permafrost is in the form of frozen organic matter, and this organic matter was literally buried into the permafrost. As erosion places sediment on the surface, organic matter at the bottom of the active layer eventually becomes frozen in the permafrost. And to illustrate what this looks like, this is frozen permafrost carbon, you might say. Pictures taken in a permafrost tunnel dug by the Army Corps of Engineers right outside of Fairbanks. This is roughly 35 meters down or underneath the surface, and the carbon here is on the order of 30,000 years old. On the left is frozen tree roots and tree trunks. Now it's not fossilized, it's actually just frozen. And on the right is frozen grass. Sometime in the past, the ice melted, this grass tumbled down into it, it refroze, and it's been there ever since. Now, there's a lot of gray dust in this particular tunnel, and so everything's kind of gray, but if you look real closely at that grass, it's actually still green. So it's 30,000 years old and still green. Now, as long as this organic matter stays frozen in the permafrost, it's stable. Nothing will happen. But if you thaw out the permafrost, the organic matter will thaw out too. And this will release carbon dioxide and methane into the atmosphere. When you do this, it'll amplify or accelerate warming due to the burning of fossil fuels. Now, you're probably wondering how much will be released and when. There are 15 published estimates of future emissions from thawing permafrost, and they're shown here. The vertical axis is just the name of the team that did the work, so you don't have to look too closely at that. On the horizontal axis is cumulative emissions in gigatons of carbon for 3 different time periods, by 2100, by 2200, and by 2300. Now, the first thing to notice here, looking at the blue bars there, by 2100, there's a wide range of possibilities here. But the thing to look at is the mean of all these estimates. The mean is 120 gigatons by 2100. Now, is this a lot? Well, this is anywhere between 5 or 40% of fossil fuel emissions by 2100. So it's not necessarily huge, but nor is it negligible. Now, you may ask, how will this impact global climate? We did a number of calculations, and we estimate this will increase the global temperature by roughly 0.2 degrees. Now, for comparison, the basis of negotiation of the global climate change treaty is 2 degrees above pre-industrial warming of 2 degrees above pre-industrial levels. So this is roughly 10%. Again, not necessarily huge, but not negligible either. Now, another thing to see when looking at this plot is that a number of the teams extended their projections out to 2200 or 2300. And you notice right off that the bars for after 2100 are as big or bigger than before 2100. What this means is roughly 60% of the total emissions from thawing permafrost will occur after 2100. Now, this has some really long-term effects. Now, the thing to get out of this is that this whole process is essentially irreversible. Once you thaw out the permafrost, you really can't refreeze it. Once the organic matter thaws out and decays away, there's no way to put it back into the permafrost. And once you turn on these emissions, you really can't turn them off, and they persist for centuries. Now, you're probably asking, what on earth can we do about this? Well, we worked with the UN to publish a report and made some very specific recommendations that are practical and things that we can do right now. The first thing we recommended was that the IPCC do a special assessment focusing just on permafrost emissions and their impact on global climate. The reason for this is that none of the projections of future climate in the latest assessment report actually account for emissions from permafrost. Therefore, they all underestimate the total temperature increase over time. You may ask, by how much? Well, roughly 0.2 degrees in 2100. We also recommended that nations with permafrost develop nationalized permafrost monitoring networks. Now, I didn't get into this because of time constraints, but there are whole areas the size of Texas and the permafrost regions that have absolutely no monitoring in them at all. And lastly, we recommend that nations develop adaptation plans to identify at-risk infrastructure and to try to make plans to minimize economic impacts. Now, I'd like to end my talk with some really big picture thoughts. Now, scientifically, the debate over climate change is over and has been for 10 to 13 years. The real debate today is, what are we going to do about it? Now, there's only one surefire way to stop global climate change, and that's to reduce emissions. Now, in this country, the new EPA rules on power plant emissions is a good first start, but alone will not achieve our goals. As a nation, I think we need to invest in reducing the cost of renewable energy. We need to invest in reducing the cost of energy conservation, and we need to foster innovation with basic public policy like tax breaks. This will create an environment where the average consumer, like me, will naturally pick the low carbon option because that's the best economic option available. I'm convinced that if we could harness these basic market forces, that we will simultaneously stop global climate change and expand our economy. Global climate change is a huge challenge, but it is also a huge opportunity to create American industries with American jobs on American soil. Thank you.